They're lying to you about the moon. Billions of dollars are being poured into lunar programs right now, and not one person in charge will tell you the simple fact: humans can never truly live there. Not in 10 years, not in 100. The moon isn't humanity's next home. It's a graveyard waiting to happen. And here is a question. If you could send a message to future humans 10,000 years from now, what would you say? Let us know in the comments. I will pin the most creative answer. Now let's begin. Picture yourself standing on the lunar surface. You're inside the most advanced spacesuit humanity has ever created, weighing over 200 pounds on Earth but feeling lighter in the moon's 1/6 gravity. You look up and see Earth, a blue marble suspended in the absolute blackness of space. No atmosphere softens its edges. No twilight eases the transition between day and night. The sun hangs like a blazing furnace in the sky, and the landscape around you glows with an otherworldly brightness. Your first thought might be wonder. Your second thought should be fear, because in that moment, you're being bombarded by radiation that would kill you in weeks without protection. The dust beneath your feet contains microscopic shards sharper than broken glass, charged with static electricity that makes it cling to everything you touch. The temperature swings from hotter than boiling water to colder than Antarctic winter. And beneath your boots lies a world with gravity so weak that your bones begin deteriorating the moment you arrive. Let me take you on a journey through the science that reveals why the moon, despite being our closest celestial neighbor, might remain forever beyond our reach as a true home. We're going to explore real research, actual missions, and the latest discoveries that paint a picture very different from the optimistic videos you see online. You'll learn about the invisible threats that Apollo astronauts encountered but didn't fully understand. You'll discover why the very soil of the moon might be toxic to human tissue. And you'll see how the moon's environment creates a cascade of problems that compound each other in ways that make long-term habitation not just difficult, but potentially impossible. This matters because billions of dollars and countless human hours are being invested in lunar programs right now. The Artemis program aims to establish a permanent human presence on the moon by the 2030s. China and Russia are planning their own lunar base. Private companies are designing habitats and mining equipment, but are we being honest about the risks? Are we acknowledging the fundamental obstacles? Or are we so captivated by the romance of space exploration that we're ignoring the warnings written in the very atoms of the lunar surface? I'm not here to crush dreams, I'm here to illuminate reality. Because understanding the true challenges isn't pessimistic, it's essential. When we comprehend why the moon resists human habitation, we gain deeper appreciation for the remarkable achievement of the Apollo missions. We develop more realistic timelines for space exploration, and most importantly, we ask better questions about where humanity should actually focus its efforts to become a spacefaring civilization. The moon has been humanity's companion for 4.5 billion years. It's shaped our tides, stabilized our planet's rotation, and inspired countless generations to look upward and dream. Ancient cultures worshipped it, poets wrote odes to it, scientists studied it through telescopes for centuries before we finally touched its surface in 1969. That moment when Neil Armstrong took his famous first step seemed to announce that humans could go anywhere. The moon was conquered, Mars would be next, the galaxy awaited. But 57 years have passed since that historic landing, and no human has returned. Why? The usual answer involves political will, funding priorities, and shifting national interests. These factors are real, but they don't tell the complete story. The deeper truth is that even during the Apollo missions, astronauts encountered problems that we still haven't solved. They came home with symptoms that scientists are only now beginning to understand. They reported phenomena that seemed minor during short visits but would become catastrophic during long-term stays. The Apollo astronauts were test pilots, military veterans, and engineers chosen for their calm under pressure and physical excellence. They were also incredibly lucky. Their missions lasted between 8 and 12 days. They spent only a few hours actually walking on the lunar surface. They returned before the full effects of the lunar environment could manifest in their bodies. Even so, they experienced issues that should have raised more alarm than they did. Spacesuits became contaminated with dust that proved almost impossible to remove. Astronauts developed respiratory irritation after breathing air in their lunar module that contained trace amounts of this dust. Equipment degraded faster than predicted. Cameras jammed, visors scratched, seals wore down. These weren't just minor inconveniences, they were warnings. The moon was showing us its teeth, even during our brief visits, and now, as we plan to return not for days but for months or even years, we need to confront what those warnings actually mean. Before we dive into the specific challenges, I want you to think about what makes a place habitable, not survivable, habitable. There's a crucial difference. With enough technology, you can survive almost anywhere for a limited time. The International Space Station proves this. Astronauts live in low Earth orbit for 6 months or longer, and they do it successfully. But they're not thriving, they're maintaining. Their bones weaken, their vision deteriorates, their immune systems struggle. They can only stay for so long before the human body says enough. If this exploration into the harsh realities of space fascinates you, make sure to hit that subscribe button and give this video a thumbs up. It helps more people discover these important truths about our cosmic neighborhood, and it keeps this channel growing so I can bring you more content like this. Your support truly matters. The moon presents all the challenges of the International Space Station, with additional obstacles that are, in many ways, more severe. Low Earth orbit sits within Earth's protective magnetosphere, a magnetic bubble that shields the station from much of the dangerous radiation streaming through space. The moon has no such protection. Low Earth orbit allows for rapid evacuation if something goes catastrophically wrong. A crew can be back on Earth within hours. The moon is 3 days away at minimum, and launch windows depend on orbital mechanics that can't be rushed. The International Space Station can be resupplied regularly with fresh food, water, medicine, and replacement parts. Sending cargo to the moon costs exponentially more in fuel, time, and money. So, when we talk about making the moon a human home, we're not talking about a camping trip or even an Antarctic research station. We're talking about creating a completely self-sufficient habitat in one of the most hostile environments imaginable, with no realistic prospect of quick rescue or easy resupply. This requires solving not just engineering problems, but fundamental challenges rooted in physics, chemistry, and human biology. And as you're about to discover, some of these challenges might not have solutions at all, at least not with anything resembling current or near-future technology. Let's start with something that sounds benign but might be the single most dangerous substance on the lunar surface, something so ordinary in name that it barely registers as a threat: dust. You hear that word and probably think of the grey film on your furniture or the clouds kicked up by a passing car. Lunar dust is nothing like that. It's a weapon forged by 4 billion years of cosmic bombardment, and it might be what ultimately prevents humans from ever truly colonizing the moon. On Earth, dust is relatively harmless. Sure, it can trigger allergies or asthma in sensitive individuals, but for most people, it's just a nuisance. Earth dust has been weathered by wind and water for millions of years. The particles are rounded, smoothed, and relatively inert. You can brush it off your clothes, vacuum it from your carpet, and wash it down the drain. It's annoying, but it's not dangerous. Lunar dust is a completely different beast. Imagine taking shards of volcanic glass, grinding them down to particles finer than talcum powder, then giving each one jagged edges, sharper than any razor blade. Now imagine These particles carry a static electrical charge that makes them cling to every surface they touch with an almost magnetic intensity. Finally, imagine this dust has been sitting in hard vacuum, bombarded by solar radiation and cosmic rays for billions of years, making it chemically reactive in ways that Earth materials simply aren't. That's lunar dust, and it's everywhere. The technical term is regolith. It covers the entire lunar surface to depths ranging from several meters to potentially dozens of meters in some locations. Unlike Earth soil, which contains organic materials and moisture, lunar regolith is created purely by mechanical destruction. For over 4 billion years, meteorites and micrometeorites have been smashing into the Moon's surface at speeds of thousands of miles per hour. Each impact shatters rock into smaller and smaller fragments. With no atmosphere to slow these projectiles or weather to smooth the resulting debris, the Moon's surface has been ground into an incredibly fine, incredibly sharp powder. During the Apollo missions, astronauts described this dust as behaving unlike anything they'd encountered on Earth. Harrison Schmitt, the geologist who walked on the Moon during Apollo 17, said it smelled like spent gunpowder when they brought it back into their lunar module. This wasn't imagination. The dust was actually reacting with the oxygen and moisture in their breathable atmosphere, releasing compounds that created that distinctive smell. Other astronauts reported that it tasted metallic. Some experienced sneezing and respiratory irritation, symptoms that thankfully faded after they returned to Earth. But here's what's terrifying when you dig into the recent research published by NASA and independent scientists in 2025 and 2026. That respiratory irritation wasn't just a temporary annoyance. Studies conducted on simulated lunar dust using pulverized basalt, which closely mimics the real thing, show that when these particles enter lung tissue, they cause inflammation, similar to what coal miners experience with black lung disease. The jagged edges physically tear microscopic damage in the delicate alveoli, the tiny air sacs where oxygen enters your bloodstream. The chemical reactivity triggers immune responses. And because the particles are so fine, they can penetrate deep into the lungs where the body has difficulty removing them. Research published in Nature in 2022 showed that lunar dust simulants can damage DNA in human lung cells. The study exposed human cell cultures to particles that matched the size, shape, and mineral composition of real lunar regolith. Within hours, researchers observed cellular stress, DNA breaks, and markers of inflammation. The dust particles are so small and so sharp that they can pierce cell membranes. Once inside, the reactive surface chemistry, created by eons of space weathering, generates free radicals, those unstable molecules that damage cellular machinery and can lead to cancer. Now imagine you're living in a lunar habitat for 6 months. Despite your best efforts, dust gets tracked inside every time someone goes out on an extravehicular activity. It clings to spacesuits with that static charge, and it's almost impossible to remove completely. Apollo astronauts reported spending significant time trying to brush dust off their suits before re-entering their module, and they still brought substantial amounts inside during their short missions. In a long-term habitat, this dust would accumulate. You'd breathe it day after day. You'd ingest particles on your food. It would get into the water recycling systems, the air filtration units, and every mechanical component of your life support. NASA researchers at the Johnson Space Center in Houston have developed what they call dirty labs, specifically to study this problem. In January 2026, National Geographic published an extensive report on these facilities where scientists are testing an experimental technology called an electronic dust shield. The concept uses electric fields to repel charged dust particles, essentially creating a force field around spacesuits and equipment. Early results show promise in laboratory conditions, but deploying this technology on the actual Moon, where dust behavior might differ in ways we haven't fully predicted, remains uncertain. Here's something that really drives home how serious this is. Amy Fritz, a dust mitigation researcher at Johnson Space Center, described lunar dust simulant as having an adhesive quality unlike anything else. When you plunge your hand into it, the powder coats your skin completely. Shaking doesn't dislodge it. Brushing barely helps. It clings with almost supernatural persistence. And this is the substance that would cover every square inch of your lunar base, your rovers, your solar panels, your greenhouse windows, and eventually, despite every precaution, the inside of your lungs. The physiological effects go beyond respiratory damage. Studies on rats exposed to airborne lunar dust simulants, published in Frontiers in Immunology in February 2025, revealed systemic immune alterations. The researchers exposed rats to respirable-sized lunar dust particles for 4 weeks, then examined the animals at various intervals afterward. They found changes not just in the lungs, but in blood markers indicating that the immune system was mounting a body-wide response. White blood cell distributions shifted, inflammatory cytokines increased. The body was treating the dust as a persistent threat, maintaining a state of heightened immune activation that, over time, could lead to chronic inflammation and increased disease risk. Think about what this means for a permanent lunar settlement. Chronic inflammation is linked to cardiovascular disease, neurodegenerative conditions, cancer, and accelerated aging. If simply living in a lunar environment means breathing trace amounts of this toxic dust daily, residents would face elevated health risks that compound over time. And unlike terrestrial environmental hazards, you can't just move to a cleaner neighborhood. The dust is everywhere, as fundamental to the lunar environment as air is to Earth. But let's say we somehow solve the dust problem. Maybe we develop perfect air filtration systems. Maybe we coat everything in those electric shields. Maybe we design airlocks with such sophisticated cleaning procedures that not a single particle makes it inside. We'd still face another invisible killer that's even more insidious and harder to defend against: radiation. Speaking of hostile environments in our solar system, I created another video exploring why Mars will always be lethal for humans. Mars has many of the same radiation challenges as the Moon, but with additional complications that make it potentially even more dangerous for long-term habitation. If you're fascinated by the obstacles facing human space exploration, I think you'll find that video equally eye-opening. You can find it linked in the description or in the cards above. On Earth, we're protected by 2 crucial shields. The first is our atmosphere, a 100-mile thick blanket of gas that absorbs and scatters much of the incoming radiation from space. The second is our magnetosphere, the magnetic field generated by Earth's molten iron core that deflects charged particles from the solar wind. These 2 shields work together to reduce the radiation dose at Earth's surface to levels that life can tolerate and even thrive under. Sure, we still need sunscreen, and yes, high-altitude flights increase exposure slightly, but overall, Earth is a radiation-safe environment. The Moon has neither of these protections. It has no atmosphere worth mentioning. A few stray atoms of helium and argon drift above the surface, but calling it an atmosphere is like calling a handful of gravel an ocean. And the Moon has no magnetic field, at least not a global one. Some localized magnetic anomalies exist, remnants of ancient geological processes, but nothing that provides meaningful protection. This means that anyone on the lunar surface is exposed to the full intensity of space radiation, with only their habitat walls and spacesuit materials standing between them and particles traveling at nearly the speed of light. Space radiation comes in 2 primary forms. First, there's solar particle events, sudden eruptions from the sun that blast enormous quantities of protons and other charged particles into space. These events are unpredictable and can occur with little warning. During a major solar particle event, radiation levels can spike to lethal doses within hours. Apollo astronauts were fortunate that no major events occurred during their missions. If one had, the thin walls of their lunar module would have provided minimal protection. Today, we have better monitoring and could potentially predict some events hours or even days in advance, but that doesn't eliminate the danger. If you're outside during a solar particle event on the Moon, even for a short extravehicular activity, you could receive a radiation dose equivalent to multiple years of natural background exposure on Earth. The second form is galactic cosmic rays. These are high-energy particles, mostly protons and atomic nuclei, that originate from exploded stars across the galaxy. They stream through space constantly, day and night, year after year. Unlike solar radiation, which varies with the Sun's 11-year activity cycle, galactic cosmic rays provide a constant background dose that accumulates relentlessly. And here's the cruel twist. The more shielding you add, the more complex the problem becomes. You might think that shielding against radiation is simple. Just add more material between you and space, right? Build thicker walls, wear heavier spacesuits, and the problem is solved. Unfortunately, radiation physics doesn't work that way. When high-energy particles slam into shielding materials, they don't just stop. They interact with the atoms in those materials, and these interactions create secondary radiation. Imagine a cosmic ray particle striking an aluminum wall. The collision shatters atomic nuclei in the aluminum, creating a shower of neutrons, gamma rays, and other particles. Some of these secondary particles are actually more dangerous to biological tissue than the original cosmic ray. This phenomenon is called spallation, and it means that conventional shielding can sometimes make the radiation problem worse, not better. The materials we typically use for spacecraft construction, like aluminum and titanium, are lightweight and strong, but they're terrible for radiation protection because they produce significant secondary radiation when bombarded by cosmic rays. Scientists have explored alternative shielding materials. Hydrogen-rich substances like water, polyethylene, and other plastics are better because hydrogen atoms absorb particle energy more effectively without producing as many dangerous secondaries. Some proposed lunar habitat designs include water-filled walls that serve double duty as radiation shielding and resource storage. Others suggest burying habitats under meters of lunar regolith, using the Moon's own soil as a radiation barrier. Research published in Nature Astronomy in July 2024, using the Red Moon model, which stands for Radiation Environment and Dose on the Moon, calculated exactly how much shielding would be required for different scenarios. The results are sobering. On the lunar surface with no shielding, astronauts would receive about 66% of the radiation dose they'd experience in open interplanetary space. You might think that's good news that the Moon itself provides some shielding. But here's the catch. As you go beneath the surface, the dose initially stays high or even slightly increases before it finally drops to negligible levels at about 3 meters depth. 3 meters. That's nearly 10 feet of lunar regolith needed to reduce galactic cosmic ray exposure to safe levels. Now think about what that means for construction. You'd need to excavate enormous quantities of material, build your habitat, then pile all that regolith on top. We're not talking about a thin layer of dirt on the roof. We're talking about creating artificial hills over every structure. The equipment required to move that much material would be massive, heavy, and expensive to transport to the Moon. And every time you want to expand your base or build a new module, you'd need to repeat the process. But let's say we accept that challenge. We build underground. We tunnel into the sides of craters or excavate into the regolith plains. We create a subsurface city where radiation levels are acceptable. We've now solved one problem but created several others. Underground habitats would require extensive life support systems with no natural light, no direct visibility of the outside environment, and increased psychological stress from confinement. Humans evolved under open skies. Extended isolation in underground bunkers, even on Earth, causes psychological strain. On the Moon, 3 days from home with no possibility of stepping outside into something resembling natural environment, the mental health challenges could be severe. And even if the habitat shields you adequately, what about extravehicular activities? Working on the lunar surface is essential. You need to maintain equipment, conduct scientific research, mine resources, and build new structures. Every hour spent outside is an hour of radiation exposure. The study using red moon data calculated that during baseline conditions, using the last 2 solar cycles from 2000 to 2022 as reference, astronauts could work on the surface for limited periods. But if a major solar particle event occurred while someone was outside, they could receive a radiation dose in a single event that exceeds the annual exposure from galactic cosmic rays. That kind of acute exposure would require immediate crew replacement and medical treatment. Current space agencies use career dose limits for astronauts. NASA's limit is designed to keep an astronaut's increased lifetime cancer risk below 3%. Sounds reasonable until you realize that spending extended time on the lunar surface would eat through that career limit rapidly. An astronaut might only be able to participate in 1 or 2 lunar missions before reaching their maximum allowable exposure for their entire career. This dramatically limits workforce development and institutional knowledge. You can't build an experienced lunar exploration corps if each person can only go once or twice. The radiation problem also extends to equipment. Electronics are vulnerable to radiation damage. High-energy particles can flip bits in computer memory, causing errors or crashes. They can degrade solar panels, reducing power generation efficiency over time. They can damage sensors, cameras, and communication systems. Spacecraft designers use radiation-hardened components for critical systems, but these are heavier, more expensive, and often less capable than standard electronics. A lunar base would need extensive redundancy and regular replacement of radiation-damaged equipment, adding to the logistical burden. Now let's talk about something that seems less dramatic than dust or radiation, but is equally fundamental to the question of whether humans can truly live on the Moon: gravity. Or more precisely, the lack of it. The Moon's gravitational pull is approximately 1/6 of Earth's. This has obvious advantages. Objects weigh less, making construction easier. Astronauts can jump higher and carry heavier loads. Launch vehicles need less fuel to escape the Moon's gravity well. On the surface, these seem like pure benefits. But human physiology evolved under Earth's gravity over hundreds of millions of years. Every system in your body, from your cardiovascular system to your bones, to your inner ear balance mechanisms, is calibrated for 1g, Earth's gravitational acceleration. When you reduce that to 1/6 g, those systems don't just adjust smoothly, they begin to malfunction in ways that become more severe the longer the exposure continues. We know this from studying astronauts on the International Space Station, which is effectively a microgravity environment. In microgravity, bones lose density at a rate of about 1 to 2% per month. This happens because bones are living tissues that constantly remodel themselves in response to mechanical stress. When you walk, run, or even just stand on Earth, your bones experience forces that signal them to maintain their strength. Remove those forces, and the body interprets this as a signal that the bones are overbuilt for the current environment. Osteoclasts, cells that break down bone tissue, become more active than osteoblasts, cells that build new bone. The result is net bone loss, a condition similar to severe osteoporosis. The International Space Station has extensive exercise equipment. Astronauts spend 2 to 3 hours every day working out on specialized treadmills, resistance devices, and bicycles designed to provide mechanical loading on their skeletons. Even with this rigorous exercise regimen, they still lose bone density. When they return to Earth, it takes months or even years to recover, and some studies suggest that certain bone properties never fully return to pre-flight levels. Older astronauts who fly multiple missions may face increased fracture risk later in life. Now here's the critical question. Would the Moon's 1/6 gravity be enough to prevent this bone loss, or would it simply slow the rate compared to microgravity? We don't know. No human has spent more than 3 days on the Moon. The Apollo astronauts weren't there long enough for measurable bone density changes to occur. We have no data points between microgravity and full Earth gravity. It's possible that 1/6 g provides enough mechanical loading to maintain bone health. It's also possible that it doesn't, and lunar residents would experience the same progressive skeletal deterioration as space station astronauts, just slightly slower. This is not a trivial unknown. If lunar gravity proves insufficient to maintain bone health, every resident of a lunar base would face a degenerative condition that worsens with time. Imagine living somewhere knowing that every month you stay, your bones become more fragile, your fracture risk increases, and your eventual return to Earth's gravity becomes more dangerous. Hip fractures, vertebral compression fractures, and long bone breaks would become increasingly likely. For a permanent settlement, this would mean that no one could actually stay permanently. Everyone would need to rotate back to Earth periodically to allow their skeletons to recover. But bones aren't the only concern. The cardiovascular system also adapts to reduced gravity, and not in good ways. On Earth, your heart has to pump blood upward against gravity to supply your brain. Your leg veins have one-way valves that prevent blood from pooling in your lower extremities. In reduced gravity, these systems become less critical. The heart doesn't have to work as hard. Blood redistributes toward the upper body and head. Initially, astronauts experience facial puffiness and nasal congestion as fluid shifts from their legs to their torso and head. Over weeks and months, the cardiovascular system remodels. The heart becomes slightly smaller and less muscular because it doesn't need the same capacity. Blood volume decreases because the body interprets the fluid shift as excess volume. When astronauts return to Earth after long-duration space flights, they often experience orthostatic intolerance, difficulty standing without feeling dizzy or faint. Their cardiovascular systems have deconditioning to the point where they struggle to maintain blood pressure against Earth's gravity. Some astronauts need wheelchair assistance immediately after landing, even though they were healthy and active in space just hours before. Again, we don't know if 1/6 gravity would prevent this or merely slow it. If lunar residents experience progressive cardiovascular deconditioning, the implications are serious. Medical emergencies requiring strong cardiovascular function, like fighting infections or recovering from injuries, would become more dangerous. And if someone spent years on the Moon, would their heart and blood vessels adapt so completely to the low-gravity environment that returning to Earth becomes medically impossible? Could we create a population of humans who are physiologically trapped on the Moon, unable to come home without severe health consequences? Then there's the immune system. Research conducted on astronauts aboard the International Space Station has shown that spaceflight weakens immune function. The reasons are complex and not fully understood, but they likely involve stress, radiation exposure, altered sleep patterns, and direct effects of microgravity on immune cells. Astronauts on long-duration missions show reduced T-cell function, altered white blood cell counts, and reactivation of dormant viruses like herpes simplex and varicella zoster, the virus that causes chickenpox and shingles. In the confined environment of a spacecraft or lunar habitat, infectious diseases could spread rapidly. If your immune system is compromised, even common bacterial or viral infections become more dangerous. And unlike Earth, where you can be rushed to a well-equipped hospital, lunar medical facilities would be limited. Severe infections could become life-threatening simply because advanced medical intervention isn't available. Imagine appendicitis on the Moon. On Earth, it's a routine surgery. On the Moon, it's a potential death sentence if not caught early And if surgical capabilities are limited, the combination of radiation exposure damaging DNA in immune cells, the stress of isolation and confinement, and the possible effects of lunar gravity on immune cell function creates a scenario where lunar residents might face chronic immune suppression. This wouldn't just make them more vulnerable to infections. It would increase cancer risk, slow wound healing, and potentially accelerate aging. Let's shift our focus to something that seems mundane but becomes critically important when you're trying to survive far from Earth. Resources, specifically water, oxygen, and food. On Earth, we take these for granted. Turn on a tap, water flows, open a window, breathe air, walk to a store, buy groceries. Simple. On the Moon, every single molecule of water, every breath of oxygen, and every calorie of food represents a complex logistical and engineering challenge. Early lunar mission concepts assumed we'd simply bring everything from Earth. Launch rockets loaded with supplies, land them on the Moon, and keep the base stocked through regular cargo flights. This approach works for short-term missions with small crews. The Apollo astronauts brought everything they needed. But when you start thinking about permanent habitation with rotating crews of dozens or even hundreds of people, the math becomes impossible. Let's run some numbers. An average human needs about 2 liters of water per day just for drinking. Add water for food preparation, hygiene, and medical needs, and you're looking at roughly 3 to 4 liters per person per day in a very austere scenario. A crew of 50 people would need between 150 and 200 liters daily, which is roughly 55 to 73,000 liters per year. Water weighs 1 kilogram per liter. That's 55 to 73 metric tons of water annually just for one crew of 50 people. Current launch costs to the Moon are estimated at thousands of dollars per kilogram, even with next-generation rockets like SpaceX's Starship that promise to reduce costs. Sending tens of thousands of kilograms of water to the Moon every year would cost hundreds of millions of dollars, and that's just water. Add food, spare parts, medical supplies, scientific equipment, and everything else needed to sustain a base, and the annual resupply cost becomes astronomical, literally and financially. This is why the concept of in situ resource utilization, using materials already on the Moon, has become central to lunar exploration plans. The big discovery that changed the conversation was finding water ice on the Moon. For decades, scientists thought the Moon was completely dry. The Apollo samples showed no water. The prevailing theory was that the Moon formed from debris created when a Mars-sized object collided with early Earth, and the heat from that collision would have vaporized any water. Then, starting in the late 1990s and early 2000s, missions like Lunar Prospector, Chandrayaan-1, and the Lunar Reconnaissance Orbiter found evidence of hydrogen concentrations in permanently shadowed craters near the lunar poles. Hydrogen is a component of water, and these detections suggested that water ice might be hiding in areas where sunlight never reaches, and temperatures plunge to some of the coldest in the solar system, as low as -400 degrees Fahrenheit or -240 degrees Celsius. This discovery was celebrated as a game changer. Water on the Moon could be extracted, purified, and used for drinking. It could be split into hydrogen and oxygen through electrolysis, providing breathable air and rocket fuel. It would dramatically reduce the amount of material that needs to be shipped from Earth, potentially making long-term lunar habitation economically feasible. NASA's Artemis program specifically targets the lunar South Pole, partly because of these water ice deposits. But before we get too excited, let's examine the reality of extracting and using lunar water ice. First, we don't actually know how much water is there or how accessible it is. The detections from orbit measure hydrogen, not water directly. That hydrogen could be in the form of water ice, or it could be bound in minerals, or it could exist as individual hydrogen atoms implanted in the regolith by the solar wind. The concentration is estimated to be somewhere between 0.5 and 5% by weight in the richest deposits. That means you'd need to process between 20 and 200 kilograms of frozen regolith to extract 1 kilogram of water. The permanently shadowed craters where this ice exists are among the most challenging environments on the Moon. They're in perpetual darkness, making operations difficult. They're extremely cold, which creates problems for equipment. Metals become brittle, lubricants freeze, batteries lose efficiency. You'd need to develop mining equipment that can operate in these conditions, excavate the frozen regolith, transport it to a processing facility, heat it to release the water, capture the vapor, and purify it to standards safe for human consumption or use in life support systems. Every step of this process requires energy, and lots of it. Where does that energy come from? Solar panels are the obvious choice, but in permanently shadowed craters, there's no sunlight. You'd need to place solar arrays on crater rims or nearby elevated terrain that receives sunlight, then transmit that power to the mining operations. Or you could use nuclear reactors, which would require transporting highly regulated nuclear material to the Moon and managing all the associated safety and political challenges. Let's assume we solve the technical problems and establish a functioning water extraction operation. We're now processing tons of regolith, dealing with that dangerous lunar dust we discussed earlier, running energy-intensive heating and purification systems, and maintaining complex equipment in one of the harshest environments imaginable. And at the end of all that effort, we're getting water that still needs to be recycled and reused with extreme efficiency because, even with local extraction, we can't afford to waste any. The International Space Station recycles about 93% of its water. Urine, sweat, even the moisture in exhaled breath is captured, filtered, and purified back into drinking water. It's a remarkably efficient system, but that 7% loss still needs to be replaced. On the space station, that's feasible because resupply missions arrive regularly. On the Moon, every percentage point of loss matters more because the cost and difficulty of replacement is so much higher. A lunar base would need to achieve even better recycling rates, potentially 98 or 99%, to be sustainable. That level of efficiency is at the edge of what current technology can achieve. Oxygen faces similar challenges. Humans need about 800 grams of oxygen per day for breathing. For 50 people, that's 40 kilograms daily, or about 14.5 metric tons per year. Bringing that from Earth is prohibitively expensive. The same water ice we discussed could provide oxygen through electrolysis, but there's another potential source. The lunar regolith itself is about 40% oxygen by weight, bound up in minerals like silicon dioxide and iron oxide. Extracting this oxygen requires heating regolith to extreme temperatures, over 900 degrees Celsius or 1650 degrees Fahrenheit, and using chemical or electrochemical processes to separate the oxygen from the minerals. This is called molten regolith electrolysis, and while it works in laboratory conditions, scaling it up to industrial production on the Moon is a massive undertaking. You'd need to continuously mine and process regolith, consume enormous amounts of energy, and manage the leftover mineral byproducts. Here's a detail that often gets overlooked. When you extract oxygen from lunar regolith, you're left with silicon, iron, aluminum, and other metals. These could be valuable for construction and manufacturing, which is great, but in the short term, you're producing large quantities of material that you need to do something with. You can't just pile it up indefinitely. You need to either use it, store it, or dispose of it in a way that doesn't interfere with operations. On Earth, industrial waste management is a major challenge even with our extensive infrastructure. On the Moon, it's an entirely new problem. Now let's talk about food. This is where the challenges become even more fundamental. Humans can't synthesize nutrients from raw elements like plants can. We need complex organic molecules, proteins, fats, carbohydrates, vitamins, and minerals in specific forms. On the International Space Station, all food is brought from Earth. It's freeze-dried, vacuum-packed, and carefully balanced for nutrition. Resupply missions arrive every few months with fresh shipments. This works for crews of 6 or 7 people on missions lasting 6 months. It doesn't scale to permanent lunar habitation. The only sustainable option for long-term food production is agriculture, growing plants on the moon. This sounds straightforward until you consider what plants need. They need water, which we've already discussed, is challenging to obtain. They need nutrients like nitrogen, phosphorus, and potassium. They need carbon dioxide for photosynthesis. They need light, preferably sunlight or artificial lighting with the right spectrum. And they need a growing medium, soil or some equivalent, that provides physical support and contains the necessary nutrients. Lunar regolith is not soil. It contains no organic matter, no nitrogen, no beneficial microbes. It's chemically reactive and contains minerals that could be toxic to plants. Scientists have conducted experiments trying to grow plants in lunar regolith simulants with mixed results. Some hardy species can germinate and survive, but they grow poorly and show signs of stress. The plants essentially treat the regolith as toxic waste, activating genes associated with stress responses similar to how they'd react to heavy metal contamination. To create functional agricultural systems on the moon, you'd need to either extensively modify the regolith with nutrients and organic matter brought from Earth, or construct hydroponic and aeroponic systems that don't use soil at all. These systems grow plants in nutrient-rich water solutions or nutrient mist using artificial lighting in controlled environments. They're highly efficient and can produce significant yields in small spaces, but they're also complex, energy-intensive, and require constant monitoring and maintenance. The plants still need carbon dioxide. On Earth, atmospheric CO2 provides this. On the moon, you'd need to capture carbon dioxide exhaled by humans and algae or generated by other biological processes, then deliver it to the plants in controlled concentrations. You'd also need to manage humidity, temperature, and lighting cycles. A single equipment failure, a pump breakdown, a lighting malfunction, a temperature control error could kill an entire crop. And unlike Earth, where you can buy food while you recover from agricultural setbacks, a crop failure on the moon could mean starvation if reserves aren't sufficient. There's also the psychological importance of food. Astronauts on long missions consistently report that food is one of the most important factors for morale. Eating the same freeze-dried meals day after day becomes depressing. Fresh food, even simple things like lettuce or tomatoes, has psychological value far beyond its nutritional content. A lunar base would need to provide not just calories and nutrients, but food, diversity and quality that maintains psychological health. This adds another layer of complexity to agricultural planning. Energy is the foundation that everything else rests on. Without reliable, abundant energy, you can't extract water, produce oxygen, grow food, maintain life support systems, power equipment, or communicate with Earth. The Moon offers 2 primary energy options, solar power and nuclear power. Each has significant limitations. Solar power on the Moon seems ideal at first glance. No atmosphere means no clouds, no weather, and intense sunlight. Solar panels would receive unfiltered sunlight and could, in theory, generate more power than they do on Earth. The problem is the lunar day-night cycle. Each lunar day lasts about 29.5 Earth days. That's nearly 15 days of continuous sunlight followed by nearly 15 days of complete darkness. During the lunar night, solar panels generate zero power. Your base would need to rely entirely on stored energy, either batteries or fuel cells, for 2 weeks straight. Current battery technology couldn't support this without requiring battery banks so large and heavy that transporting them to the moon would be economically prohibitive. Advanced energy storage systems using technologies not yet operational at scale would be necessary. One proposed solution is to build solar arrays on the peaks of eternal light, elevated terrain near the lunar poles that receives nearly continuous sunlight due to the moon's minimal axial tilt. These locations exist, but they're rare and not necessarily near the best spots for water ice extraction or base construction. You'd need extensive power transmission infrastructure, cables, or microwave power beaming systems to get energy from the solar arrays to where it's needed. And even the peaks of eternal light aren't perfect. They still experience brief periods of shadow, and the sunlight arrives at very low angles, reducing efficiency. Nuclear power could solve the day-night problem. Small modular reactors designed for space applications could provide continuous baseload power regardless of sunlight. NASA has been developing a fission surface power system specifically for lunar applications, with the goal of delivering a reactor that could produce tens of kilowatts continuously for years. For context, tens of kilowatts is enough to power several houses on Earth, but a lunar base with life support, water extraction, oxygen production, agriculture, and scientific equipment would need much more, potentially hundreds of kilowatts or even megawatts. Nuclear power comes with its own challenges. Reactors are heavy. They require shielding to protect nearby humans from radiation. They generate heat that needs to be dissipated, which is harder in vacuum where you can't use convective cooling. They need maintenance and eventually require refueling or replacement. And there are political and safety concerns about launching nuclear material from Earth, even though such launches have been done before for deep space missions. There's also the question of redundancy. A lunar base can't afford a single point of failure in its power system. If the reactor fails and there's no backup, everyone dies within hours as life support systems shut down. You'd need multiple independent power sources, which multiplies the mass, complexity, and cost of the energy infrastructure. Every kilogram of equipment sent to the moon represents thousands of dollars in launch costs and takes up space that could be used for other critical supplies. Let me paint a picture of what daily life might actually look like on a lunar base, assuming we somehow overcome all the technical challenges we've discussed. You wake up in a small, windowless sleeping compartment buried under meters of regolith for radiation protection. The air smells recycled, which it is, cycled through the same filters thousands of times with the faint chemical tang of scrubbers, removing carbon dioxide and trace contaminants. You've been on the moon for 3 months and you're beginning to notice that moving feels different. Your muscles are adapting to the low gravity, becoming weaker, even though you exercise daily on specialized equipment. After a breakfast of rehydrated food and perhaps some fresh lettuce from the greenhouse, you check the day's schedule. There's maintenance work on the water extraction equipment. One of the pumps is showing signs of wear from processing abrasive regolith slurry, and it needs inspection before it fails completely. You suit up for an extravehicular activity, a process that takes nearly an hour with help from another crew member. The space suits are marvels of engineering, but they're also bulky, uncomfortable, and require meticulous checking of every seal and system. One small leak could kill you. You cycle through the airlock, and as the pressure drops, you feel the suit inflate around you, stiff and restrictive. The outer door opens and you step onto the lunar surface. The sunlight is blindingly intense and the shadows are absolute black. There's no diffusion, no atmosphere to soften the contrast. The horizon is sharp and close, only about 1.5 miles away due to the moon's smaller size compared to Earth. The landscape is grey and lifeless, beautiful in an alien way, but utterly devoid of the colours and textures your brain evolved to find comforting. You make your way to the water extraction facility, each step kicking up small clouds of dust that hang briefly before settling in the low gravity. The dust coats your suit. You can see it accumulating on your gloves and boots. You know that when you return inside, despite cleaning procedures, some of this material will come with you. It always does. You've noticed that several crew members have developed persistent coughs. The medical officer says it's probably minor respiratory irritation from dust exposure, but everyone remembers the research about lung damage and DNA breaks. The pump inspection reveals that the impeller blades are worn down faster than expected. The abrasive regolith, even in slurry form, is grinding away the metal. You'll need to replace the component, but the spare parts inventory is limited. Each replacement part that gets used is one less available for future failures. You make a note that the next resupply mission, scheduled in 4 months, needs to include additional pump components. If critical equipment fails before that resupply arrives, operations could be severely impacted. Back inside after 3 hours of surface work, you spend another 30 minutes in the airlock going through decontamination procedures. Brushing, vacuuming, and using the experimental electrostatic cleaning system to remove as much dust as possible. It helps, but it's not perfect. You can still see fine grey powder in the creases of your suit. Once you finally remove the suit and stow it properly, you're exhausted. Extravehicular activities are physically and mentally draining in ways that are hard to explain to people who haven't experienced them. The afternoon is spent on administrative tasks. Reviewing water recycling efficiency reports, the system is currently running at 97.3% recovery, which is good, but still means the base is slowly losing water that needs to be replaced from ice mining operations. Oxygen production from regolith processing is meeting current needs, but the furnace is consuming more power than projected, which means less power available for other systems. Every resource allocation is a careful balancing act with no margin for error. Evening brings a group meal in the common area, one of the few times the crew gathers socially. Morale has been declining. 2 crew members had a serious argument last week over something trivial, a symptom of the psychological stress from isolation and confinement. The base psychologist has been conducting regular counseling sessions, but there's only so much she can do. Everyone knew intellectually that being on the moon would be challenging, but the reality of living in a small, enclosed, dangerous environment for months on end wears on people in ways that are hard to predict or prepare for. After dinner, you have an hour of personal time. Some crew members video call their families on Earth, though the 2.5-second time delay makes conversation awkward. Others read, watch shows, or exercise again. You find yourself looking at images of Earth, oceans and forests and clouds, things you won't see again for another 3 months when your rotation ends and the next crew relieves you. You think about the fact that your bone density has decreased measurably since you arrived, your cardiovascular system is deconditioning, your immune markers are concerning the medical team, and despite all the precautions, you've accumulated a radiation dose equivalent to several years of life on Earth. The question that keeps occurring to you is whether this is sustainable, not just technically, but humanly. Can people really live this way permanently? Can children be raised in this environment? The thought of childhood on the moon is almost unfathomable. A child born on the moon would develop in 1/6 gravity. Their bones and muscles would form in an environment completely different from what human physiology expects. Would they even be able to visit Earth? The gravitational stress might be too much for a skeleton and cardiovascular system that never adapted to 1G. There's also the ethical dimension. Is it right to create a generation of humans who are essentially trapped on the moon, unable to experience the world their species evolved on? Would they resent their parents for that choice? These aren't just philosophical questions. They're practical considerations that any permanent lunar colony would have to confront. Let's talk about the economics for a moment, because ultimately, any permanent human presence on the moon needs to make some kind of economic sense. The Apollo program cost approximately $153 billion in today's money. That brought 12 successful missions, 6 lunar landings, and 12 humans walking on the moon for a combined total of about 3 days and 8 hours. The return on investment was primarily scientific knowledge, technological advancement, and geopolitical prestige. These are valuable, but they're not the kind of returns that sustain permanent operations. For a lunar base to be economically viable long-term, it needs to either produce something of value that can be sold, or it needs to serve a purpose that justifies continuous government or private funding. The proposals generally fall into a few categories. Scientific research using the moon as a platform for astronomy, astrophysics, and planetary science. Resource extraction, mining the moon for rare elements, or helium-3 for potential fusion reactors. Tourism, allowing wealthy individuals to visit the moon. And strategic positioning, maintaining a presence for national prestige or potential military applications. Each of these faces serious obstacles. Scientific research on the moon has value, but much of what we want to study can be done more cheaply with robotic missions or from Earth orbit. The far side of the moon is an excellent location for radio astronomy because it's shielded from Earth's radio noise, but building and maintaining a crewed observatory there would be extraordinarily expensive compared to automated facilities. Resource extraction sounds promising until you examine the economics carefully. What resources on the moon are valuable enough to justify the cost of extraction and transport back to Earth? Rare Earth elements exist on the moon, but they're also becoming less rare on Earth as new deposits are found and recycling improves. Helium-3, often cited as a potential fusion fuel, exists in lunar regolith, but we don't have working fusion reactors yet, and we won't know if helium-3 fusion is practical for decades. Mining materials for use on the moon itself for construction and manufacturing makes more sense, but that only works once there's already a significant lunar economy to supply. Tourism might be the most realistic near-term economic driver. If launch costs come down significantly and safety improves, there could be a market for lunar visits among the ultra-wealthy. But tourism requires infrastructure, hotels, transportation systems, entertainment, and safety margins much higher than scientific missions. A single tourist death would likely end the entire industry. And tourism doesn't create a self-sustaining economy. It brings money in, but it doesn't produce goods or services that can be traded or that reduce dependence on Earth. The strategic positioning argument is that nations will maintain lunar presences for the same reasons they maintain Antarctic research stations or remote military bases: national prestige, scientific claims, and the desire not to be left behind by competitors. This could sustain some level of lunar activity, but it's unlikely to support large permanent populations. Antarctica, despite being far more hospitable than the moon, has only temporary populations of researchers who rotate in and out. No one lives there permanently, and no children are born and raised there. Here's something that doesn't get discussed enough in the excitement about lunar exploration. The moon is geologically dead. Earth is a living planet in the geological sense. Its molten core generates a magnetic field. Tectonic plates shift, creating mountains and ocean basins. Volcanoes release gases that replenish the atmosphere. This geological activity is part of what makes Earth habitable. It recycles nutrients, regulates temperature through the carbon cycle, and maintains atmospheric composition over geological timescales. The moon has none of this. Its core is mostly solidified. There's no plate tectonics, no volcanism that we know of in the past several hundred million years. The surface is essentially frozen in time, only changing through meteor impacts and the slow accumulation of space weathering. This geological death means there's no natural recycling of elements, no replenishment of resources, no dynamic processes that might create concentrated deposits of valuable materials. On Earth, Many of our most valuable mineral deposits were created by geological processes. Hydrothermal vents concentrate metals, sedimentary processes concentrate phosphates. Volcanic activity creates specific mineral formations. The Moon had some of these processes billions of years ago when it was geologically active, but not recently enough or extensively enough to create the kinds of rich, accessible deposits that make mining economical on Earth. Lunar resources are spread diffusely through the regolith and bedrock, which means any extraction operation requires processing enormous quantities of material for relatively small returns. There's also the question of what happens when something goes catastrophically wrong. On Earth, if there's an emergency at a remote research station, rescue can usually arrive within hours or at most a few days. Injured personnel can be evacuated to hospitals with advanced medical facilities. If a fire breaks out, fire suppression systems and emergency responders can contain it. If there's a structural failure, people can evacuate to the surrounding environment, which, while potentially harsh, is at least breathable and survivable in the short term. On the Moon, there's no emergency evacuation to a safe environment. Outside the habitat is vacuum and death. If there's a catastrophic pressure loss, everyone in the affected section has seconds to get to spacesuits or sealed compartments before they lose consciousness. A fire in the enclosed, oxygen-rich environment of a lunar habitat would be terrifying. The fire suppression systems would need to work perfectly because you can't just open doors and windows to ventilate. The atmosphere is precious and can't be vented carelessly into space. Medical emergencies present particularly difficult challenges. The nearest fully equipped hospital is 250,000 miles away, and even in an emergency, getting someone from the lunar surface back to Earth takes at least 3 days with current technology. During Apollo 13, when an oxygen tank exploded on the way to the Moon, the crew was able to survive by using the lunar module as a lifeboat and performing a carefully calculated trajectory that brought them back to Earth. It was desperate and dangerous, but possible. If a similar emergency happened on the lunar surface, the options would be far more limited. Imagine a crew member suffering a major medical crisis, a heart attack, a stroke, acute appendicitis, severe trauma from an accident. The base medical facility would have a doctor or paramedic and emergency medical supplies, but not surgical suites, not advanced imaging equipment, not the full range of pharmaceuticals and blood products available at a major hospital. Some conditions that are survivable on Earth with proper treatment would be death sentences on the Moon simply because the necessary medical intervention isn't available. There's also the psychological factor in emergencies. On Earth, even in dangerous situations, there's a sense that help can come, that you're part of a larger civilization with vast resources. On the Moon, you're isolated in the most profound sense. The crew is all you have. If the people around you can't solve a problem, it doesn't get solved. That psychological weight, the knowledge that you're truly on your own, affects decision-making and stress responses in ways that are difficult to study or prepare for. Let's consider the long-term evolutionary implications if humans somehow did establish permanent populations on the Moon. Evolution operates through natural selection over many generations. Organisms that are better adapted to their environment survive and reproduce more successfully. In the lunar environment, the selection pressures would be radically different from Earth. Humans who naturally maintain bone density better in low gravity would have advantages. Those whose cardiovascular systems adapt more efficiently to reduce gravitational stress would fare better. Individuals with more radiation-resistant cellular repair mechanisms, though this is largely not heritable in useful ways with current genetics, would have lower cancer rates. Over many generations, these selection pressures could, in theory, create a population that's increasingly adapted to lunar conditions and potentially less adapted to Earth conditions. This isn't science fiction speculation, it's basic evolutionary biology. But here's the unsettling part. The time scale for significant evolutionary adaptation is typically thousands to tens of thousands of generations for complex traits. Even fast human evolution, like lactose tolerance in dairy farming populations, took thousands of years. We're not talking about a population that adapts to the moon in a few centuries. We're talking about a process that would take tens of thousands of years to produce meaningful physiological changes. Long before natural evolution could adapt humans to the moon, we'd either need to use genetic engineering to deliberately create humans better suited to low gravity and high radiation, which raises profound ethical questions, or we'd need technological solutions to modify the environment and protect biology. The first option, genetic modification, crosses lines that many societies consider unacceptable. The second option, perfect technological life support for millennia, requires a level of engineering reliability and social continuity that humanity has never achieved. Consider also the cultural and social evolution of a lunar population. If a community lived on the moon for generations, they would develop their own culture, identity, and perhaps even languages distinct from Earth. Their daily experiences, their environment, their challenges would be completely foreign to Earth humans. Would they consider themselves human in the same sense? Would they want to maintain connections with Earth? Or would they see themselves as a separate people? History shows us that isolated populations diverge. Islands develop unique cultures, remote valleys produce distinct languages. A lunar colony, by far the most isolated human population ever, would almost certainly develop in unexpected directions. And if that population became self-sustaining, if they no longer needed supplies from Earth, what would their relationship with Earth be? Would they be a colony, a trading partner, an independent nation, or something entirely new in human political organization? There's something deeply melancholic about all of this. The moon has captivated human imagination for millennia. It's featured in poetry and mythology across every culture. We've told stories about the moon, worshipped it, used it to track time and guide navigation. When the Apollo astronauts first walked on the moon, it was one of humanity's greatest achievements, a moment of collective pride and wonder. The dream of returning permanently, of building homes and cities on that silver surface, has inspired generations. But the more we learn, the more we understand the immense gulf between the dream and the reality. The moon is not a new world waiting to be settled like the Americas or Australia were to European explorers. Those lands had air, water, life, resources, and familiar gravity. The moon has none of these things. It's fundamentally hostile to life in ways that no place on Earth has ever been. Even the most extreme earthly environments, the Antarctic ice sheets, the deepest ocean trenches, the driest deserts, are paradises compared to the lunar surface. Some might argue that this is defeatist thinking, that humanity has always overcome obstacles through ingenuity and determination. They'd point to previous technological achievements. We crossed oceans in wooden ships, we built cities in deserts, we learned to fly, we split the atom. Each of these seemed impossible until we did them. Why should the moon be different? The difference is one of fundamental compatibility. Wooden ships floating on water is challenging engineering, but it works with natural principles. Oceans are made of water, wood floats. You're working with nature, not against it. Building cities in deserts is difficult, but air is breathable, gravity is normal, and water can be transported from elsewhere. Flying required understanding aerodynamics and building engines, but once mastered, it uses natural atmospheric properties. Living on the moon requires fighting against fundamental physical reality every single moment. Gravity isn't just lower, it's permanently wrong for human physiology. The radiation environment isn't just dangerous like a toxic waste site, it's unavoidable without massive shielding that requires industrial-scale construction. The lack of atmosphere isn't just an inconvenience, it means that every breath of air, every drop of water, every degree of temperature control requires active technological systems that can never be allowed to fail. Perhaps most telling is this: Despite decades of space exploration, despite billions of dollars invested, despite tremendous technological progress, we still haven't maintained a human presence beyond low Earth orbit. The International Space Station orbits just 250 miles up, close enough that emergency return to Earth is possible within hours. We haven't gone back to the Moon in over 50 years, not because we lack the technology. Fundamentally, we could recreate Apollo with modern systems, but because the cost and risk have been judged not worth the return. Every few years, new lunar exploration plans are announced. NASA's Artemis program aims to return humans to the Moon in the late 2020s. China has announced ambitious lunar plans. Private companies talk about lunar tourism and mining. These programs may succeed in landing humans on the Moon again. They might even establish temporary bases that operate for months or years. But establishing a permanent, self-sustaining human population? That remains, based on everything we currently understand about physics, biology, and engineering, an extraordinarily unlikely outcome. There's a concept in systems engineering called failure modes and effects analysis. You examine every component of a system, identify how it could fail, and assess the consequences of that failure. For most terrestrial systems, many failures are inconvenient or costly, but not catastrophic. Your car breaks down, you call for help. Your home's heating system fails, you use space heaters and call a repair service. Your water main breaks, the city shuts off the water and fixes the pipe. Life continues. On a lunar base, almost every system failure mode leads to the same ultimate consequence: death. The life support system fails, you die. The power system fails, life support stops, and you die. The habitat springs a leak, you die. The airlock malfunctions during an EVA, you die. The thermal control system breaks down, you either freeze or overheat and die. The water recycling system fails, you run out of water and die. The food production system collapses, you starve and die. You can build in redundancy, backup systems for backup systems, but each layer of redundancy adds mass, complexity, cost, and its own potential failure modes. And no amount of redundancy can eliminate risk entirely. There's always some cascade of failures that overwhelms the backups. On Earth, that cascade usually has to be extensive before it becomes life-threatening, and rescue is often possible. On the Moon, the cascade can be much shorter, and there is no rescue beyond what the crew can accomplish themselves. This creates a psychological burden that's difficult to overstate. Astronauts on the ISS know they're in danger, but they also know that in an emergency, they can board a Soyuz or Crew Dragon capsule and be back on Earth within a few hours. That psychological safety valve exists. On the Moon, you can't just go home when things get scary. You're committed to being there until the next transfer window, which might be weeks or months away, and even then requires a functioning spacecraft and launch capability. Studies of isolated and confined environments on Earth, submarines, Antarctic research stations, remote oil platforms, show consistent patterns of psychological stress. Initial excitement gives way to monotony. Social tensions emerge, sleep disturbances become common, some individuals develop anxiety or depression, and these are environments where people know that the outside world, while potentially harsh, is at least fundamentally survivable, and that evacuation is possible if absolutely necessary. A lunar base would be isolated and confined to a degree that no human population has ever experienced. The Antarctica research stations have the harshest conditions, but even there, you can step outside without a spacesuit during summer. You can see the sky and horizon. You breathe fresh air, even if it's cold. On the Moon, stepping outside means hours of preparation, bulky spacesuits, and constant awareness that you're in an environment that's actively trying to kill you. The psychological impact of never being able to simply go outside and take a walk cannot be understated. There are proposals to address this. Build large enough habitats that they don't feel confining, include gardens and green spaces to provide psychological benefits, use virtual reality to simulate Earth environments, carefully screen crew members for psychological resilience, provide extensive communication with Earth, entertainment, and recreational activities. All of these help, but they're treating symptoms rather than addressing the fundamental issue. Humans evolved in open, complex, Earth gravity environments with day-night cycles, weather, ecosystems, and social structures involving hundreds or thousands of people. A lunar base can't replicate any of that. Let's examine the transportation infrastructure required for a permanent lunar presence. Getting to and from the Moon isn't like catching a flight. It requires some of the most complex and powerful machinery humans have ever built. The Apollo program used the Saturn V, still the most powerful rocket ever to fly successfully. Each Saturn V cost about $1.2 billion in today's money and was used once. The entire rocket was expendable, nothing was reused. Modern efforts focus on reusability to reduce costs. SpaceX's Starship is designed to be fully reusable and could theoretically reduce the cost per launch by orders of magnitude compared to Apollo-era technology. But even with optimistic projections, launching 100 tons of cargo to the Moon would cost tens of millions of dollars. A permanent base might need hundreds or thousands of tons of equipment and supplies delivered over years. That's billions of dollars just in transportation, before considering the cost of the equipment itself. And every launch has a failure rate. Current commercial space launch reliability is roughly 98 to 99% for mature systems. That sounds good until you realize it means 1 or 2 failures per 100 launches. If you're launching 100 cargo missions to support lunar operations, statistically, you'll lose 1 or 2 of them. That's not just a financial loss, it's potentially mission-critical equipment that doesn't arrive, forcing difficult decisions about priorities and capabilities. Crew transport adds another layer of risk. Human-rated spacecraft need higher reliability standards than cargo launchers, but they still can't achieve perfect safety. The Space Shuttle had 2 catastrophic failures in 135 missions, roughly a 1.5% failure rate. That's an unacceptable level for routine transportation. Modern crew vehicles aim for much better, but even a 1 in 500 or 1 in 1,000 failure rate means that over hundreds of crew rotation flights, fatalities are statistically likely. Every person who signs up to go to the Moon knows they're accepting risk. Astronauts have always been test pilots and explorers willing to put their lives on the line. But there's a difference between accepting risk for a pioneering mission that advances human knowledge and accepting risk for what's essentially a routine job if the Moon becomes a permanent workplace. Would people raise families on the Moon knowing that every time a parent takes a transport back to Earth for any reason, there's a measurable chance they won't come back? Would children grow up with that uncertainty? The mechanics of living on the Moon also involve countless small challenges that add up to major quality of life issues. Simple things that we don't think about on Earth become complicated engineering problems. Take a shower. On Earth, water flows, drains, and gets carried away by plumbing. In lunar gravity, water doesn't flow predictably. It forms floating globules or sheets. The ISS uses special shower bags and vacuum systems to contain and recycle water during bathing. It's functional, but far from the refreshing experience of a normal shower. Laundry is another example. On the ISS, there's no laundry. Clothes are worn until they're too dirty, then disposed of on cargo ships that burn up in Earth's atmosphere. New clothes arrive with resupply missions. A lunar base would need actual washing machines designed for low gravity, recycling the wash water, dealing with lint and debris that doesn't settle naturally, and drying clothes in an environment where evaporation doesn't work normally. These seem like trivial problems until you realize that wearing dirty clothes for extended periods affects hygiene, health, and morale. sleep is affected by the environment in ways that are difficult to fully simulate before you're there. The ISS has a day-night cycle programmed into its lighting, but astronauts still report sleep disturbances. The Moon's day-night cycle is 29.5 days long. Would you keep Earth's 24-hour cycle with artificial lighting, essentially ignoring the natural environment? Or would you try to adapt to the lunar cycle, staying awake for extended periods during lunar day when solar power is available and entering reduced activity during lunar night? Either choice has consequences for human biology, which is deeply tied to circadian rhythms. Communications with Earth face a time delay of about 1.3 to 2.6 seconds each way, depending on Moon-Earth distance. That's short enough that live conversation is possible, but long enough to be noticeable and occasionally awkward. You ask a question, wait 3 to 5 seconds for a response. It's manageable but psychologically significant. You're reminded constantly that you're not having a normal conversation, that you're far away, that the connection could be lost if technical problems arise. And sometimes the connection is lost. The Earth needs to be above the lunar horizon for direct radio communication. If you're on the far side of the Moon, you need relay satellites to maintain contact. Any interruption in that relay chain means communication blackout. A solar flare that disrupts electronics could cut you off from Earth for hours or days. During those periods, you're entirely alone with whatever situation you're facing, no possibility of advice or assistance from mission control. Then there's the question of governance and law. Who makes the rules on a lunar base? The Outer Space Treaty of 1967, which most spacefaring nations have signed, states that celestial bodies are not subject to national appropriation and that activities in space should benefit all humanity. It's a noble principle but vague when it comes to practical governance. If a US company builds a lunar mining operation, who enforces safety regulations? Who resolves disputes between crew members from different nations? What legal system applies if a crime is committed? Antarctica provides a partial precedent. The Antarctic Treaty System designates Antarctica as a scientific preserve, with territorial claims frozen and activities regulated internationally. But Antarctica has no permanent population and limited economic activity. The Moon, if it develops economic value, will face pressures that Antarctica hasn't. Companies will want resource extraction rights, nations will want strategic positioning, individuals will want property rights. The legal and political frameworks to handle these issues don't exist yet, and developing them will require international cooperation on a scale that has historically been difficult to achieve. There's also the question of environmental protection. The Moon is a pristine scientific environment that records billions of years of solar system history. Every landing disturbs regolith, every base construction alters the landscape. Mining operations would transform large areas. Do we have an obligation to preserve parts of the Moon in their natural state for scientific and historical value? Should certain areas, like the Apollo landing sites, be protected as heritage sites? These questions are starting to be discussed. But there's no binding international framework yet. Some argue that the Moon is lifeless and therefore environmental concerns are irrelevant. But that misses the point. The Moon's scientific value lies partly in its pristine state. Contamination from Earth organisms, chemicals from industrial operations, and physical disturbance from construction all degrade that scientific value. Once we've industrialized the Moon, we can never return it to its untouched state to answer questions we haven't thought to ask yet. Speaking of extreme environments and cosmic realities, if you found this exploration of the Moon's hostile conditions fascinating, you'll definitely want to watch my video called The Terrifying Truth About How Cold Space Really Is. It dives deep into the temperature extremes of space and the physics behind why the vacuum of space is so fundamentally hostile to life. The video is at the left side of the screen. It's a perfect companion to this discussion about the harsh realities of living beyond Earth.